Hello and welcome everyone. Can you hear me or see me? Just give a thumbs up if you can. Alright, so there are around 10 thumbs ups right now, so that's good. So I'm visible. So just let me also check if I'm streaming on YouTube. Uh, I'll just check that and then we'll start the class. I should be doing it. Yes, I am streaming on YouTube as well. So, hello for everyone that is watching on YouTube and also on an academy. I'm Manwani, and today, in the second day of Indian Programming Camp, I'm going to be teaching you about flows. This is the sixth lecture, I think, on Division 1, right? So, it will be a 2 hour session, starting from the complete basics of flows and going up to the kind of level you require in competitive programming, at least in the basics level of flows, right? There might come some very advanced question for that you might have to study later. So today, uh, let me first introduce myself, right, for people joining in today. I'm Nishchay. Guys might know me as USORS at Code Forces or NM at CodeChef. Uh, I'm also an educator at an academy. You can find my profile from here. Good evening, Sudipan. Also, I would be checking doubts on the Unacademy chat and the YouTube chat once every like 10 minutes. So, all right. So you can put your doubts on both chats, and I will be able to see it immediately, right? So let me go over the Unacademy platform for some time, as long as people are joining in. And I won't take much time. I want to just talk about what makes us, conduct this giant programming camp for free for such a large audience, and then we just go on over to flows, right? So this Unacademy platform has free classes that you can see right now, which we are conducting for the students, and it has plus courses. For plus courses, you have to get a subscription, but what this plus courses comprise is like, let's say, a number theory or programming. It takes a courses on them, like 8 10 classes, and it totally enables you to study about those topics. So what will you get in such kind of courses? First of all, live interactive classes like you're getting right now. Uh, but these classes would be, like in a planned structure and not just a one shot, like one class on flows or something. It would be, starting from the basics of graphs and going up to the really advanced stuff as well. Like Pulkit is taking right now, he has taken 2 courses on graphs, right? I've taken one on number theory and the other on computational geometry. So it totally, all of the concepts that are in computational geometry, you can study that with those 10 lectures, and also some problem solving sessions as well. Of course, doubt support, you will be getting doubt support 24/7 by us and many TAs. Relevant problems at CodeChef, you can practice those. I hand select those. So there are many great educators. These educators, you guys might know them. They are also teaching in this programming camp, right? Nishchay, Manwani, Pulkit Chhabra, and we have Tanush Khattar, a two-time world finalist. You might know him as a great educator, right? So he's also at an academy. Arjun, a bronze medalist, and IOI, Deepak, a world finalist. So we have this team and also many talented TAs, right? And these are the kind of topics that will be covered, or have been covered already. We are also, doing many different courses. These are the type of courses that are in an academy. These are the forums at which there will be problems and problem solving. And this is the pricing structure, right? For 1 month it's 6,000, but it has some discount if you go to select larger durations of subscriptions like 12 months or 6 months. But you can apply a code NM for a 10% off, and you will get 10% off on any of the courses that you like to apply, right? So with this uh, said, let us go on over to flows. So I just want to check how many people know of graphs before this, right? Let me actually make a poll here. So just answer true or false in the chat, right? Uh, it will be a poll of 30 seconds. Do you know graphs, like a basic of graphs? Uh, like a basic, like BFS, DFS, might even know Dijkstra, right? Because I'm going to mention Dijkstra at one point. Not exactly Dijkstra, but I guess you can say, yeah, it would be Dijkstra. So if you do not know graphs, this class is just after that, right? 4% of people do not know graphs. So you should go in Division 2 or Division 3 type of classes. Those are more basic. Division 3 is the ultimate basic. Division 2 is then the next intermediate level in which you learn about the basics of graphs. And this is the Division 1 class, which is advanced, and you will get to know about flows, which are after graphs, right? So, yeah, 96% of you know about graphs, but just as for the 4%, this class wouldn't be very helpful for you, right? So, let me start with flows. I'm going to start from the absolute basics of flows, right? So, what do we understand by flows? And what kind of problem it tackles? So, there are many problems that can be modeled on flows, right? I will, as this session goes on, I will tell you some example problems which you cannot even start to think that this can be modeled as a flow problem, right? But the most basic kind of flow problem is something like you have an infinite tank, sort of, where there is a lot of water, right? And there are pipes going on from there. This pipe has a capacity of, let's say, S1 cubic meter per second, right? Cubic meter per second means like how much water is flowing through that in per second time. So it has a capacity of S1. Now from this one, it has many junctions, right? One is at S2, one is at S3, one is at S4. From here as well, there is another pipe, and from here it goes on different junctions, right? So this is kind of a graph like structure, as you can see. There are many pipes, and these pipes are also unidirectional, right? Because the water can flow only from one point to the second point. Of course, in here it is written that the uh, capacity of this pipe is S1 meter cubic meter per second, but it might be that the whole S1 cubic meter per second is not being used here. Let's say only 1 cubic meter per second is used when the capacity is 2. That might happen. It might even happen we are not using this pipe at all. But more than S1 cubic meter per second cannot flow through here, right? So after all this, it comes to an infinite reservoir, like which is like an infinite tank, and it is going to all flow into here, right? So the flow problem, basically the main problem that comes here is trying to find out what is the maximum flow from this infinite source to this infinite deposit, right? From the source to the destination, how much flow is going to happen. So that is the problem that we are going to solve. One small request, can you please skip the very basics, because due to the time runs out when the actual good part comes in, the lecture doesn't remain very fruitful for people who are actually here just for the advanced and non-trivial ideas. I'm not going to go on many non-trivial ideas. I'm going to go on scaling method and stuff like that, but uh, this is also going to be a 2-hour session, right? I remember, I think you are mentioning my last class in which I kind of rushed from the Zor part, but that was a 1-hour session and I kind of timed it wrongly, so sorry about that. But this is going to be a 2-hour session, so I think I can cover everything here, right? And also many people here are trying to learn about flows from the very start, and they do not know anything about flows, so I would have to go on the many basics as well. Let me actually just have a poll. So do you know anything about flows? Do you want me to, go over the trivial stuff as well? Just let me know in this poll. Here is the poll, right? And you can answer in here. And by the basics, I mean the first kind of algorithm that comes here, the Ford-Fulkerson algorithm. So there are many people around, more than the majority of people who want to learn. So let me, go through that quick, not quickly, but given enough time, and then we'll go on to the advanced stuff, right? So the maximum flow problem, this is an example of that problem, right? So we have a capacity of 5 in this pipe, 4 in this pipe, 3 in this pipe, 6 in this pipe, 8, 1, 2, and 5. An example of a flow, right, is this kind of structure where I'm sending 2 cubic meter per second from here, then 2 from here, then 2 from here, right? Then I'm sending, because this node has total of 4 cubic meter per second on it, so I'm sending 4 here, I'm sending 1 here, I'm sending 3 here, and then lastly I'm sending 1 here, right? So this is an example of a flow. This is not the optimal value of the flow, but this is one example of a flow structure, right? Basically, let me just override these values so it's more readable, right? So this is one flow. What are the kind of things that we notice, right? Here is also some flow which is 0, right? The flow here is basically first of all, each value which is going through an edge, let us call that f of e, that is the flow of that edge, right? This should be greater than equal to 0 and should be less than equal to the capacity of that edge. This is the first rule, right? And the second rule, the more important rule, that the flow which is incoming on a node, right? The summation of, let me write this in a better method. The second rule is the flow of edges where E is incoming on a node X, right, is equal to E of outgoing edges on node X, right? Also, just give a thumbs up if you do understand all of these topics. If you have a doubt at any point, you can use a confused phase on the chat, right? So this is the two important points. First is this point, right, that the input flow should be the output flow. The main rule is ever rule. I'm not sure about that. And then there is this rule that the flow should be greater than equal to 0 and should be less than equal to the capacity, right? So how do we calculate the maximum flow? This is one flow, but this is not the maximum. This is not the optimal flow that we can have here, because in this one, the total flow is only going to be 4, right? From the source, I am having 4 amounts of flow going from here, and at the destination as well, I'm having 3 plus 1 equal to 4 flow coming in, right? So the Ford-Fulkerson algorithm, which is the first algorithm that you learn for how to calculate the maximum flow, is this algorithm, right? In this Ford-Fulkerson algorithm, what we do, for every directed edge, such a directed edge here, right? In this flow system, it's a system of directed edges. So it's a graph G where each edge is directed and has some weight, right? So directed graph and weighted graph, and should be never mind, let's just skip that. So for every directed edge, add another reverse edge with weight 0. So in the initial graph, as you can see here, for the 5 edge, I'm adding edge 0 towards the back. For the 3 edge, I'm adding 0. For the 4 one, I'm adding 0. So here I'm adding a reverse edge with weight 0. And what do these edges now finally represent? These represents how much more flow we can route through it, right? So what do we mean by that? in this system, from 1 to 2, I can add 5 more flow to this pipe, right? Let's imagine that as a pipe. Then I can add 5 more flow through from 1 to 2, because there is an edge from 1 to 2 with the weight 5. And from 2 to 1, I cannot add any more flow currently, right? So the weight there is going to be 0, because I cannot add any more flow there from 2 to 1, right? These values are going to change. Like, let's say if at the final graph, let's say we reach a level like this, where from 1 to 2 there is a flow going from 1 to 2 with the value 2. Then this edge is going to be 3 and this edge is going to be 2, right? Let me actually draw this. So in Ford-Fulkerson algorithm, what we have is, we have rounds. For each round, find some path from source to destination with minimum weight edge on this path. Basically, let's say I go from here, I cannot go from there. Let's go here, right? I found one path like this, from 1 to 4 to 4 to 5 to 5 to 6, right? So here the flow is going to be the flow of this path is going to be the minimum weight edge in this path, which is 1, right? That is a limiting edge. So then when we flow it like this, what we are going to do, let me show this on a new graph, right? Let me add all the nodes, 1, 6, 4, 5, 2 and 3. So there was a 5 here, there was a 0 here, there was a 6 here, and there was a 0 here. I'm just gonna take some time, sorry for this. I should have put this in the slides. Just wait a second, right? So in this graph, what we are about to do is, we are going to add a flow of 1 through this path, right? From 1 to 4, then 4 to 5, then 5 to 6, I'm going to add another flow of 1. There are a lot of confused faces in the chat, so if you can describe what is the doubt currently, I can tackle that. Let me actually first describe a round, what a round is going to be, right? Then maybe most of your doubts will get clear. So here, what I'm going to do, if I'm going to add a flow of 1 weight in this path, I'm going to remove these forward edges and instead replace them by some lesser capacity, right? What I'm talking about is, I'm going to remove this 4, this 1 and this 2, and I'm going to write instead 3, 1 and 6. And the reverse edges that I added, I'm going to use them now. I'm going to replace them with 1, 1 and 1. Did you all understand this? How am I adding one flow here? There are a lot of confused faces, right? So let me describe what is actually happening here. In the first case, let's imagine that there is no flow going from, there is no flow in any pipe, right? Why 6? Oh, yeah, it shouldn't be 6. It should be 1. I'm sorry about that. It should be 1 here, because 2 minus 1 is of course 1, right? So in the initial system, in the all of the pipes that I was talking about, there is no flow, there is no water from any pipe to any pipe, right? But I initiate a 1 cubic meter per second flow from, oh, 1 minus 1 is also 0. I'm sorry for such mistakes. I shouldn't have done that. And I think the first one is correct. So that's 3, that's 0, and that's 1, right? This is the exact system that it looks like after adding one flow from 1 to 4, 4 to 5, and 5 to 6. Now, if I have to add, now the system looks like there is a one flow from going from this system to this system, right? From 1 to 6 through this path. Now if I have to cancel these weights, right? If I'm saying, oh, in the optimal answer, this one flow is not actually going to happen, I should have cancelled this, right? So to cancel this, what I'm actually going to do, I'm going to add another flow from 6 to 1, right? And to add that flow, because from 6 there is a an edge of 1 here, edge of 1 here, and edge of 1 here, I'm going to subtract that by 1, which will give us 0, and I'm going to add 1 in the reverse edges, which is going to give the original graph, right? So the idea here is I can cancel any flow going from one node to any other node at any point of time, right? To cancel that, I just have to subtract the flow that I am going to not to cancel, but to add any flow, I'm just going to subtract the flow that I'm going to have from the weight of this edge, and I'm going to add that corresponding flow to the reverse edge, right? By that method, I can increase the flow. If I have to decrease the flow, I'm just going to do the opposite. I'm going to reduce the weight of the reverse edge, and I'm going to increase the weight of the forward edge, right? So this is one round. The one round, I'm not talking about the cancel method. I'm just talking about the forward one, right? Let me actually remove all this. This was one round in the Ford-Fulkerson method. This was one round, right? Now the flow has increased from 0 to 1, right? Did you all understand this? How the flow has increased from 0 to 1? Just give a thumbs up in the chat if now the concept is clear of what a round is doing, right? Yep. So it is clear. Let's say, let me give another example. Let's say I add one flow from this to this to this. What is the minimum weight edge in this path? It's 5, right? So I'm taking a flow of 5 from 1 to 2, then 2 to 3, then 3 to 6. So I'm going to be subtracting 5 from here, from here, from here. I'm going to be adding 5 in the reverse edge, in the reverse edge, in the reverse edge. And what's going to happen? Now my graph is going to look like, the reverse edge has weights 5, this has weight 1, this is weight 1, this has weight 0. Now this is the resultant graph after the second round, right? Now I have to find another, now the flow has increased from 1 to 6, right? This was the second round. This was the result of the second round. Now I have to find another path from which I can increase the flow, right? Now let us see. In the implementation, I would be doing some DFS on any kind of path finding algorithm, but in dry run, I have to see, like, here is a weight 3 edge, right? So I will be going from here to here. Now there is a weight 0 edge here. I cannot go here. I would have to go up, still having the minimum weight as 1. Now I'll have to go here because there is a weight of 1. I cannot go here because that has weight 0. I would have to go down, and finally I would go there, right? So this yellow line represents the path I have taken now, right? And what is the minimum weight in this path? It's 1, right? So I'm going to subtract 1 from here, right, from each of the forward ones, and I'm going to add 1 to each of the reverse ones, right? And that would result in my new graph, right? So what happens after all of the rounds like that? Some case like that happens. This is not exactly equal to what I had shown before, but let us see what we mean by this, right? So there is a flow because this reverse edge has weight 4. That means there is a let me write that by red, right? There is a flow going through this pipe with 4. Here the reverse edge has weight 3. That means this has a flow 3 going on over here. This has 6 flow going on over here. This has 3 going on, sorry, 3 going on over here. This has 1 going on over here. This has 5 going on over here. This has 1 going on over here, and this has 2 going on over here, right? So this is the final flow that looks like after we have completed all of the rounds. And how do we know that we shouldn't apply any more rounds here? Because we cannot find any more paths. In here, when we try to find more paths, right, we cannot go from 1 to 4 because the edge there has weight 0, like it doesn't have any positive edge. So our flow is not going to increase if we go down this path, right? So we would have to go from 1 to 2. Then from 2, there is 0 here, so we cannot go there, right? I would have to go down. And from 2, I cannot go to 5 because that has weight 0, right? I can only go back to 1, and I wouldn't want to have a cycle here, right? So I wouldn't also go there. So I cannot find any more paths in this graph, right? So this is our final flow structure, and this is going to be our maximum flow of the system. Did you understand how the Ford algorithm works, the Ford-Fulkerson? Just give a thumbs up in the chat if you do understand what is happening here, right? Let me look at YouTube chat as well, right? So this is the Ford-Fulkerson algorithm, which goes on in rounds. So we just have to finding paths and remove the minimum, not remove the minimum. So what's happening here? We are finding paths which has the minimum weight greater than 0, right? And then we are subtracting that minimum weight from the path that we just came, and we are adding the that weight in the reverse edges. We are doing this again and again because we would also want to have the ability to cancel some flow, right? So that is why we have the concept of reverse edges, right? So this is what is happening here, and finally we have a flow of how much? 7, because 3 plus 4 is 7, right? You can easily find out what is the maximum flow once you have the structure, and you can also easily find out which pipe has which amount of flow going from where to where. What if there was already reverse edge with some capacity? In this kind of question, we do not want to put a reverse edge with some capacity. Acha, you mean like there was something like this? Let's say that there was a node 1 and there was a node 2. This pipe had flow 5 and this pipe has flow 2. Some example like this, right? So of course one can see that the maximum flow is going to be here 5, right? So what exactly is going on here? We do not have to add another reverse edge, right? Then I guess we add a simple edge 5, 2. Yeah, basically we do not have to add a reverse edge with weight 0, because if we want to increase the flow from here to here, we can just do this -2 and this +2, and the resultant graph will look like 1, 2. There is a 7 here and there is a 0 here, and there is a flow going on from here to here with flow 2, right? If we instead had to direct the flow from 1 to 2, right, then we would subtract 5 here, add 5 here, and then finally we would have a graph that looks like this, right? And there is a flow going from 1 to 2 with 5 value. And if we have to cancel that flow that we just did, but not cancel the whole flow, but only cancel 3 units of flow, right, then we would find a path from 2 to 1, right, with 3. We would subtract 3 here and add 3 here. So now the graphs look like 3 and 4, and the flow is exactly equal to 2. This is not what happens in Ford-Fulkerson algorithm, but I'm just trying to explain what the concept of adding reverse edges mean, right? In Ford-Fulkerson algorithm, we always subtract the minimum weight edge because that is the most optimum, right? We wouldn't want to undermine our algorithm, right? What is the need of reverse edge? This is the need of reverse edge. If we want to cancel our flow, right? We do not know in the optimal flow system, the flow that we are adding currently, if that is going to be in the final answer, right? Basically, let me actually think up of one example, right? Let's say this has a pipe of capacity 1. This has capacity 1 as well. I'm not sure of an example right now. I'm sorry about that, but I will give an example where we have to cancel a flow because the flow that we chose currently is not going to be in our optimal answer, right? So to cancel such amounts of flow, we have to add a reverse edge so such that we can cancel that flow in the next part of algorithm anytime we need, right? Let me think up of a algorithm that does this. Yeah, let's leave it for right now, right? So here's a poll. So you can answer this poll and try to work your way on this system. So just calculate the flow in this system by the Ford-Fulkerson algorithm, right? So let me give you 4 options and time. Let's say 90 seconds. 90 seconds seems nice. So yeah, the options would be here. Just select the one which you think is correct. The time is 90 seconds, so you do not have to rush through the poll, right? Let me actually take a second as well. Right. So yeah, 43% of you selected the right answer. So it's the option C here, right? And if we try to, dry run this Ford-Fulkerson algorithm on this, what we're doing is this 0 basically represents that the current flow going from S to D is 0, right? But we can have a full capacity of 4, right? So first, let's try to find a simple path. Let's go here, then go here, then go here. This is one path, and the minimum weight is 5 here, right? So let me subtract 5 from here, and the reverse edge is going to have 5, right? Max flow is equal to min card. That is also true, but let me represent this is going to be, actually let me make a new graph, right, with the reverse edges. So here is a source, here is 7, this is going to be A, B, T, this is going to be C, this is going to be D, this is going to be 5, this is going to be 8, 4, 2, 5, 3, 3, 3, right? So adding the reverse edges as well. These are going to be the reverse edges. So first we selected the topmost path, which would have the flow of 5. So let's subtract 5 from here, which is going to be 0. Add 5 here is equal to 0. Minus 5 is equal to 3. Plus 5 is equal to 5. Minus 5 is equal to 2. Plus 5 is equal to 5. So this is one round of Ford-Fulkerson algorithm done, right? The second round is going to have, let's still go from the above, path, right? So the above path, this has weight 2 currently. Then this has weight 0, so it won't go there. It would go down the path like this, right? And then it can go here, right? Simply here. So 2, 3, and then 5. What is the minimum one? It is 2, right? So subtract 2 from here. So this would result in 0. Add 2, which is going to return in 7. Minus 2 is equal to 1. Plus 2 is equal to 2. Here minus 2 is equal to 3, and plus 2 is equal to 2, right? Sir, what if initial graph is undirected? That is, simple pipes are connected and water can flow anyway. Should we make it directed randomly? No, we shouldn't direct it randomly. I'm going to talk about that in 1 second. First, let me check out this example, right? So the current flow is 7, right? From 0, we went to 5, then we went to 7, adding 2. Then we should go downwards because this is already used up, right? So we go here, right? Then we can go here, and there is still 3 paths remaining here, so we can go here, right? So we would have added 2 more here, right? So minus 2, because the minimum weight here is 2. So minus 2 plus 2, minus 2 plus 2, minus 2 plus 2, which is this is going to return in 1, this is going to return in 4, this is 2, this is 0, this is 2, and this is 2, right? The graph would look something like this, right? So the current flow is 9, right? But we can add one more flow. Already 3 rounds have completed. The last flow that we are going to add is going to go from here, because there is still 2 remaining here. It is going to go from here, then it is going to go from here, and lastly it's going to go from here, right? You can see that this has all the paths that we are selecting, all the edges that we are selecting have positive weights. This is positive weight 2, this is positive weight 3, this is positive weight 1, and this is positive weight 1. The minimum weight is going to be this one or this one, so we would subtract 1 and add one more flow, which is going to result in 10. After that, we cannot find any paths that is going to result in adding more flow to our system. So we would have to terminate our algorithm at 10, right? So the final flow is going to be 10 and not 11. So the answer was C here, right? So excuse me, Sudipan, you asked me, like, what if the initial graph is undirected, right? Right now we are taking the example of just an large reservoir and going to a sink, and in between there are many pipes which are unidirectional, right? So let us go on over to what if there are undirected pipes, right? The water can flow in this direction or in this direction. We do not have to worry about we do not have to care if the water is only going to go from one direction to the other direction in this pipe, right? Which is what usually happens. So in that one, we are going to modify our Ford-Fulkerson algorithm by a little, right? In that problem, what we are going to do, we were always adding another reverse edge with weight 0, right? Let's call this as node 1. Let's call this node 2. Let's say there was a pipe going from 1 to 2 with capacity 10. We were adding a reverse edge with capacity 0, right? In this problem, we are going to add a reverse edge of exactly the same weight, of weight 10, right? What this basically means is I can either go from 1 to 2 with 10 units of flow, right? And it's going to result in this 0, and this is going to result in 20. Or I can go from 2 to 1 with weight 10, right? What is going to happen there? This is going to result in 20 and this is going to result in 0. So I can go in either direction or also go, in between these values. It's not only at the extremes. It doesn't necessarily have to happen that I'm going from 1 to 2 with the 10 units of flow. I can also go with 5 units of flow, right? So I can choose any value in between and, accordingly change my graph. So in that kind of problem where the graph is undirected, we add a reverse edge with exactly the same weight, right? In not only Ford-Fulkerson, but in a kind of general problem you see, if we have to change an undirected graph to a directed graph, we just add two edges, one going forward, one going backward, with both the equal weights, equal to the weight that was given before. So did you all understand what I'm doing here? Just give a thumbs up if you do understand. And the intuition behind this, right? All right. So let me go on to some problems where flow is used, right? Uh, the most famous kind of problem where I have personally, went to flow. Personally, I learned flow because I had to solve a problem which used maximum matching in bipartite graphs, right? So I would call this as the most used problems in computational programming, right? This is one problem where flows are used a lot. There are also edge disjoint parts and node disjoint parts. These are not used that much, but we are all gonna see what those means, right? So that you can model other questions, the special questions that are modeled in flows, you can model them yourselves, right? So in maximum matching in bipartite graphs, what I'm trying to say, a bipartite graph is basically a graph where which can be colored in two colors, where the nodes can be colored in two colors, right? Where there is no edge between two nodes with the same color, right? Implementation of Ford Fulkerson. We'll go on over to the implementation part. Let me first implementation of Ford Fulkerson. You can find many implementations of Ford Fulkerson online as well. I'm going to go on to the implementation of better algorithms because for Ford Fulkerson, you're not going to use Ford Fulkerson many times, right? You're going to use the better algorithms because let me ask you the time complexity directly. What is the time complexity going to be of this Ford Fulkerson algorithm? If anybody knows that, you can type it in the chat or you can think about it also, right? Just type it in the chat. Yeah, so Snicksana, he wrote edges into max flow, right? Because why is this happening? Uh, in each round that we are having, right? In each round, what is going to happen is we are going to increase our flow by some amount. That is for sure. We are not going to decrease our flow. We are not going to increase our flow by 0 or not change our flow. We are going to increase our flow, but that increase might be 1, right? Basically, from the previous flow, we are going to the new flow, but the increase is only going to be 1 in one round. And like this, if we go on, doing rounds, the final flow which we have, let me call that W, right? So each in each round you are doing a DFS or something like that, which is have a complexity of E plus V, or I'm just going to use E right now because I'm not going over all the nodes. I'm starting from the source node, so it's going to have a time complexity of only E, right? So the time complexity here is going to be E into W, right? So it depends on what the final max flow is going to be, which is not a good sign. Because if I have a question where the answer is going to be 10 to the power 18, right? So the time complexity, of course, would give TLE, right? Uh, it's not, this complexity is not usually happens, right? This is a very rare case, but there are cases where but they you can easily construct test cases where the time complexity is exactly this. It's rare. It doesn't happen in randomized graphs, right? But the worst case time complexity is going to be E into W. So there are going to be better alternatives which we are going to see in the final. Yeah, this is a pseudo polynomial time algorithm, right? Or an exponential basically, right? So we're going to see better algorithms, but afterwards. So I'm going to give you implementation of those, right? let us go back to what I was talking about, maximum matching in bipartite graphs. So here we have a bipartite graphs. I'm not going to go on what a bipartite graph is, because you must have known, you must know what a bipartite graph is basically. It is basically where you can separate two sets of nodes, right? And there are some edges between the first set of nodes to the second set of nodes, right? Like this. But there is no edge like this. There is no edge between uh, a pair of nodes in the same set, right? This cannot happen. So it's something like this, right? This is not directed right now. So matching means, right? Matching is the set of edges. Matching, let me talk about what matching is first, right? Matching is a set of edges which are disjoint, right? Basically, we can call this edge, and this edge. I can call this as a matching because none of these edges are touching each other. But I cannot call this as a matching, right? Because at this node there are two edges touching here in the matching set, right? So I cannot call the set of these three edges as matching, right? In this example, the maximum matching would look something like this. Maximum matching basically means the maximum set of edges which we can achieve in a matching, right? So here the maximum matching is simple. It would have a set of 6 edges, 1, 2, 3, 4, 5, 6, and it would basically, none of these edges are touching each other. So this would be the maximum matching in bipartite graphs. So did you all understand what maximum matching is, right? And then we'll see how to model this on flow, right? It is really simple, but we'll see this problem because this is the most commonly used problem, right? Just give a thumbs up if you understand the concept here, what we are trying to find. Right? If you want to know this in a problem statement kinda, imagine the first set of nodes to be some men, right? This is also a famous problem, and this to be some, some women, and these edges basically means that this man does like this girl, right? And this man also like this girl, and it likes this one, but it does not like this one because it doesn't have an edge from here to here. Similarly, from the woman's side as well, and this is also uh, bidirectional. If a man likes a girl, then the girl likes the man as well. So this is bidirectional. Now we want to know the maximum number of marriages or something like that, the maximum number of pairings that we can create, right? So the maximum number of pairings in this one is exactly going to be maximum matching, because one node or one man, let's say, cannot marry to two girls, right? We are not having a I'm not sure of the term, but we are not having multiple marriages with the same name, polygamy, right? So yeah, we are the question basically boils down to finding the maximum matching. So how to model this as a flow problem is, let me go back. Yeah, we are going to create a source node here, not yellow. Let me create red. Here is a source node and here is a destination node, right? These are two dummy nodes that we are going to create. These are not actual nodes in the problem. We are going to create two nodes like this, and then we are going to add one edge from each source node to each man, right? Like this, which has capacity 1, right? We are going to add a pipe of capacity 1 from the source to each man. Then the edges that we had before, these edges were bidirectional, but we are going to change that to be unidirectional, and we are just going to replace that with an edge of 1 capacity to here. We can also add another edge with the reverse capacity. Actually, we cannot add that, right? We can just add a unidirectional edge from a man to a woman, right? With capacity 1, simply like this. So all of the edges have been replaced by unidirectional edges, and finally we are going to add unidirectional edges from each woman to the destination node with capacity 1. Now the maximum flow in this graph is just going to be the maximum matching that we were talking about, right? The maximum flow, let us imagine the flow is going to be, we are flowing one unit from here to here, then we are flowing one unit from here to here, then we are flowing one unit to here from here. That means that we have selected this edge as a edge in our matching, right? One looks like 2. Yeah, I'm sorry about my handwriting, but basically all of the 2's that you can see here are actually 1's, right? So here, this edge is now going to be included in our matching because there is a flow going from the man to the woman, right? So this is basically how you model questions. This is a really famous problem, and how to model some problem that you have in flow problem. And because this is so famous, everybody should know this, and you should probably remember this, how to model a maximum matching problem as a maximum flow problem, right? Basically we initiate a source node, add a pipe of capacity 1 to each node in the left set. Each edge that we had initially, we are going to turn it into unidirectional from the left side to the right side, and then from the right side we are going to add an edge of one capacity to the destination, right? Increase pen size. Oh, all right, thank you. Simon says nice taste. So yeah, this is going to be our whatever the final maximum flow comes in this graph is going to be our final answer, right? Which is going to be the maximum matching. Edge disjoint parts, let us go over to the next problem, right? So let us write edge disjoint paths. This is a problem not on bidirectional graphs like we have seen in the bipartite graphs. This is a general graph which is directed, right? So let us draw a graph like this. Yeah, so here we want to know the maximum number of paths we can create, right? From 1 to 5. The maximum number of paths we can create from 1 to 5, but the edge should be disjoint, right? Basically, we should not select one edge in multiple paths. This is a really easy question to model into a flow problem, but basically what we are talking about is this thing, right? This can be one path from 1 to 5, 1 to 3, 3 to 4, and 4 to 5. This is one path. 1 to 2, 2 to 4, 4 to 5 is another path. But we cannot select both of these paths because the edge of 4 to 5 is being selected in two distinct paths, right? So we can only select either this path, or we can either select only this path, right? If we had added a system like something like this, 7 and here, now we can actually select two paths. Now the answer is not one path, it is two paths. The first path can be something like this, right? Basically 1 to 3, 3 to 4, 4 to 6, 6 to 7, and the second path can be something like this. Basically 1 to 2, 2 to 4, 4 to 5, and 5 to 7. I'm sorry about this mess. The paths that I'm talking about, let me just color them in different ways, right? This is the first path in green, and the second path is in blue, right? Did you all understand this, what the question is? We just have to select the maximum number of paths you can find from a source to destination, but a single edge shouldn't be selected in multiple paths. Here the question of how to model this as a flow problem is really easy, but this is a precursor to the next problem that I'm going to cover, right? So if you do know how to convert this into a flow problem, just type it in the chat. I think someone has already typed it. Give edge a weight of 1 and the answer is just max flow. Yeah, that is the answer. Here, whichever edge we are looking at, just actually give that a weight of 1, right? A capacity of 1. And the answer is just going, now the problem just reduces to max flow. Whatever the max flow that we can find is actually the answer, is actually the number of maximum edge disjoint paths, right? Uh, but the next problem that we are going to look at, and we are going to see how to model that as a flow problem, is node disjoint paths, which is a little more difficult, right? Here, we want to, let's take the example previously that we covered in the previous part. Here, there is also a directed graph with 1, 2, 3, 4, 5, 6, 7. Nodes numbered from 1 to 7. We want to select the maximum number of paths, but here the same node shouldn't come again, right? Like in the previous one, we selected these two paths. In apart from the source and destination, of course, this is the source. The source can come in multiple paths, and the destination can also come in multiple paths. But 4 is neither a source nor a destination, but it is coming in two paths: the blue path and the sixth path, right? Green path, not the sixth path. So it is coming in two different paths, and that is why this is not a proper node disjoint paths, right? So in this system, we can only select one node disjoint paths, right? So how to actually find the paths themselves? Is there an easy way to keep track of it with the max flow algorithm? Uh, after, in the max flow algorithm, let me answer Samar's doubt first, right? This is unrelated to related to the edge disjoint paths. How to find the edge disjoint paths, right? So it is relatively simple. Basically, after the max flow algorithm has completed, right, when you have the final flow systems and when the final edges are directed as given, right, might be that this edge has weight 0 and the reverse edge is 8, 1. Basically, you are knowing that there is a flow of 1 going on this path. That means this is in a path, right? And so you can select that this is an edge of a path, then go to the next node, right? So this also has weight 1, this also has weight 1, this also has weight 1. So you know this is part of one path. This is one path that you're following, and this is one path you're following. After this, you come to here, and there are two separate paths going from here. So you can arbitrarily just decide to where to link which path to which path, right? You shouldn't basically do like I have done. You do not have to, link this path with this path and link this path with this path, right? You can also link this path directly with this path and this path. You can just arbitrarily choose between them. At each node, you just have to link the path coming previously to a path that is going forward, right? So in the node disjoint paths, right? Just give a thumbs up if you do understand this, Samarth, how to find the paths after we have completed the algorithm. We just have to look at the flows this edges are containing, right? So let us look at node disjoint paths. Here, the people have already told about the solution, right? Split each node into two and connect them by an edge of capacity 1, right? Basically, what people are trying to say, that we had the system like this initially. So this edge is going to have maximum capacity. It's going to be of infinite flow, right? Can also do it 1. It doesn't really change the question, right? You can think that even if I have the capacity as 1, it doesn't really change the question. But I'm just going to have it infinity for the sake of our question, right? Or infinity in basically programming just means a really large number. You can just basically type it as 1e9 or 1e18, right? Then in 2, I'm going to link it with another node called 2 prime. I'm going to create two nodes from the initial node that I had, and I'm going to connect them with an edge of capacity 1, right? Similarly below 3, and I'm going to connect them with a capacity 1, 4, infinity, infinity over here. I'm going to connect this with a capacity 1 to 4 dash. Now going down, two paths, two edges of infinity size, one connected to 5, one connected to 6. 5 is connected to 5 dash with a capacity of 1. 6 is connected to 6 dash with a capacity of 1. And 5 dash and 7 dash are connected with infinity size to 7, right? I'm not splitting 1 and 7 in two different nodes because 1 and 7 are going to come in multiple paths, but I'm splitting 4, 2, 3, 5 and 6, all of the internal nodes, right? So after this splitting, the maximum flow here is going to look something like this, right? With the flow 1, because the minimum here is 1. So this is the flow that is going to be followed. This is the modeling of the node disjoint paths question to a maximum flow question. And now when we apply the maximum flow algorithm here, any of the algorithm that I'm going to teach, right, you are going to get the maximum number of node disjoint paths from this like procedure. Did you understand how I modeled it here and why is this going to work, right? This is going to work because each node is now going to come only once in our any path that it has. Because if basically what I have done when I have splitted these two nodes, like 3, let's say 3 not only had one edge coming into it, it had multiple edges coming onto it, right? So all of those edges are going to go on over the original node 3, right? And all of the outgoing nodes are going to come out from 3 dash, right? So whenever there is a path like this, right, coming in from this edge to 3 and coming out from 3 from this path, it has to go from this path as well, right? And because this small path between 3 and 3 dash has capacity 1, only one path can cross the 3 node in the initial graph, right? Only one path can cross it. That is why this algorithm works, and that is why we can model it in a max flow problem, right? What is min cut? Yeah, I'm going to go on our min cut route now and going to discuss problems based on that as well. The capacities on the original edges can also be just be 1 instead of infinity because vertex disjoint parts are also edge disjoint parts. Yeah, that is what I was talking about before. Instead of keeping them as infinity, I can also keep them as 1, right? And it is not going to change our algorithm because node disjoint paths are also edge disjoint paths, right? But it's easy to understand if I just keep them as infinity, right? So this was some examples. Of course, we are going to see many more examples and many more problems which you can model as max flow algorithms, right? The majority work that you have to do when solving a flow problem is to know how to model this as a flow problem. After you have done that, you're just going to apply an algorithm, right? Check first which algorithm suits best for this problem and then apply it and finally get the answer. Right? Now let us see the minimum cut problem, right? So the minimum cut problem is very closely related to the maximum flow problem, and we are going to see why, right? Basically a cut, let us not talk about a minimum cut, let us talk about cuts here first, right? A cut is a set of edges, right, which when removed from the graph, like let's say I'm going to remove 5 and 4, I have cut this 5 edge and I cut this 4 edge, right? After removing this edges, 1 and 6 are now disjoint. Basically, I cannot go from 1 to 6 using any set of path. That is what I mean by a cut, right? If I just remove, let's say 3, 1 and 8, I remove these 3 edges. Then this is not a cut, right? Because I can still go from 1 to 8 using this path, right? So I have to remove some kind of edges, let's say 6 or 1 or let's say 5 or 2. I have to cut at certain place such that I can also keep all of the edges in my cut. If I include all of the edges, that is also a cut, right? It cannot go from 1 to 6. Bridges is I think only a one one set of edge. This is like I can include many edges, right? And I have a specific source node that I have to separate from six node. Bridges are I think any edge that can make my graph disconnected. Here I'm specifically trying to separate 1 and 6, right? Let me explain what I mean by that. If I cut 6, 8 and 5, right? 3 is going to get separated out, right? Our graph has become disconnected, but I can still find a path from 1 to 6 like this, right? So this is not a cut. The cut is specifically which cuts from the source node to the end node, right? So the problem here is just to find the minimum weight set of edges such that it separates 1 and 6. So minimize sum of capacities of the edges removed. Yes, I just have to minimize the sum of edges which when cut will separate 1 and 6, right? Like in this example. Sorry. So here I can remove 1 and 6, right? And it would result in a cut because now 1 and 6 are totally cutted. Can I find any set of edges which when removed would also give me a cut but has the sum of weights less than 1 plus 6 or 7, which has sum of weights less than 7? I cannot find it in this one. 5 and 4. Actually, let me check. Six one is minimum, right? 5 and 4 would give us 9. Actually, just give me a second. I'm confused now, right now. Oh yeah, the answer is 6 1, right? I was confused by the 5 4 that you wrote. The answer is 6 plus 1, which is 7, right? So how does this equate with the maximum flow that we have been reading up until right now, right? All the edges with full capacity after we run max flow will form a cut? Not exactly, right? Let me talk about it and let me explain what is happening, right? So before all that, I want you to understand any flow that we are going to get, right? Any flow value, let's say I have a graph G, right, which have some edges and nodes. This is the source and lastly it's the destination. Any flow value that I'm going to get, let's us call that as F, right, is going to be less than or equal to any cut that we can get. Let us call that as C. This doesn't necessarily has to be maximum flow and this doesn't necessarily have to be the minimum cut. I'm just saying that any flow is going to be less than or equal to C, right? Alright, why does this happen, right? Let us see why does this happen. So any flow that we have, any cut that we have, right? Basically the source node would be here. Let us say it goes on to this nodes and this nodes, right? And I group this set here and I group another set here with destination in here. And I'm basically the edges that are going to be cut from S to D, right? The edges that are going to be cut, I'm putting that between the sets, right? I'm going to be cutting these 4 edges for a cut to happen between S and D, right? So I'm keeping those edges in between these sets. So the value of this is going to be C, right? The sum of capacities of this one. Let's say this is C1, C2, C3 and C4. So C1 plus C2 plus C3 plus C4 is equal to C. There can be many edges, not exactly 4. There can be one edge as well. But basically what I want to say that I'm keeping these edges in between the sets, right? So any flow that I can get, right, has to go from these edges, right? Any flow that I'm going to have, let's say the flow is going something like this, whatever in this set, something weird. Finally, it's going to go from set S1 to S2, and then from S2 it's going to have some weird behavior and finally go to T, right? So it has to go from C1, right, with some value F1. It has to go from C2 with some value F2, here with value F3, and here with value F4, right? So F1 plus F2 plus F3 plus F4 is going to be F, right? And because of the property that I talked about before, that 0 is less than equal to F of E is less than equal to capacity of E, right? That the flow is going to be less than or equal to the capacity of that edge. Basically, our flow is going to be less than equal to C. Did you all understand this? Just give a thumbs up because this is a really important property. This is the kind of intuition to know why is our minimum cut related to maximum flow, right? Because this is a slighter difficult property to understand, because I couldn't understand it at the beginning, right? How is maximum flow related to cut in any way? This is how it's related. Can you repeat it? Alright, let me repeat it, right? So I have the set of edges that I was going to cut. I have kept that in middle of two sets, and I'm including all of the nodes and edges in one set called S1, and I'm keeping all the nodes and the edges connected to the destination in the another set, which is called S2, right? This is the set corresponding to the source. This is a set corresponding to the destination. The capacities are C1, C2, C3, C4. So the cut is going to be the summation of these capacities, right? And the flow, any flow that I'm going to have from S to D is going to go from these four edges with the F1, F2 and F3 and F4, right? So the flow value is going to be F1 plus F2 plus F3 plus F4. And because of this property, that for any edge, the flow is going to be less than or equal to its capacity, right? We finally have F is less than or equal to C, or basically for a graph, any flow that we have is going to be less than or equal to any cut that we can have on that graph, right? Did you understand it, Aitra? Alright. So after this, the more important property which we are going to use is the minimum cut is nothing but the maximum flow we can get in a graph, right? Basically, the maximum flow that we have is going to be from some range to some range, right? Let's say this is the number line, right? Going from 0 to the sum of all the edges, right? Sum of all the capacities. So we can have a flow of 0, we can have a flow of 1, something like that, up until F0, right? Which is going to be a maximum flow. I can have any flow value from 0 to F0. Also, let's say the minimum cut value is C0. I can have any cut value from C0 to C, not any cut value, but the cut values are going to be between here, right? At some points here, it's going to be between C0 and the sum of all the cuts, right? What I'm trying to say is there is no gap between here. It's 0, right? This gap is 0. Basically, F0 is equal to C0. Chatur, I'm going to answer that. That is not exactly how we do it, but I'm going to answer that in a second. So did you all understand this? I'm going to give the reasoning in a second, but this is how we are going to find a minimum cut in a graph, right? And how, what is the reasoning behind this? Right? How do we know that this gap is equal to 0 and not something not equal to 0? How do we know that, right? We know that by the Ford-Ferguson algorithm or any kind of algorithm that is going to give our minimum cut, which is equal to our maximum flow, right? Let me look at this graph, right? This was the maximum flow algorithm that we applied on this graph, right? I was on this slide before as well. That's why so many of you are trying to guess it. But basically, in here, what I'm going to do, I'm going to start a DFS from this node, right? Or a DFS or a BFS or any path, not pathfinding, basically some kind of algorithm, right? And I'm going to go on all over the nodes that can be reached from the one or from the source. I'm going to go on all of the nodes such that the like the minimum weight in this path is greater than 0. Basically some positive weight path, a node that I can reach from some positive weight path, I'm going to reach there, right? I cannot reach to 4 right now because this edge is 0, right? So I'm going to go to 2 because this is 2 right now, so I'm going to go here. Then I'm going to go to 4 because this has weight 3, right? So I'm going to go here. Now I cannot go to any other node. I cannot go to 3 because this has weight 0. I cannot go to 5 because this is also weight 0, right? So here the set 1 comprises of these nodes, right? This is our set 1, and all of the nodes remaining that can comprise a set 2, right? And the edges between them, if you sum them up, that is going to be f naught is equal to c naught. I can also cut between them to have a maximum minimum cut, and this is also the value of the maximum flow, right? So Ford-Fulkerson algorithm, the final graph in Ford-Fulkerson algorithm basically gives us a minimum cut which has the value of the maximum flow, right? F naught, which is also equal to c naught. That is why I'm saying there is no gap here. This gap is actually going to be 0, right? Because we have for any graph we can create a cut which is exactly equal to the maximum flow, right? Can we find the cut edges? Yeah, cut edges are the edges going out from the set 1. Whichever nodes that we keep in this DFS, basically when we go from 1 to 2, we go from 2 to 4, we connect all of these nodes, and whichever nodes are going out of the set, right? Whichever edges are going out of the set, like 2 to 3, this edge is going out of the set. 4 to 5, this edge is also going out of the set, right? So these edges are going to be a minimum cut. That is also how we construct the minimum cut edges, right? Let me see the doubts. All the edges with full capacity after we run max flow will form a cut. Chatur, you mentioned this before. This is wrong because this is also running at maximum capacity, right? This type of thinking is wrong because not all of the edges that are running at maximum capacity are going to be inserted into our minimum cut. The edges that have been identified with this algorithm, like 6 and 1, these are the minimum cut. We are not going to insert 5 in here as well, right? After that, we talked about to find the edges of the minimum cut and take the union of the edges which have the capacity filled. Yeah, that is basically what we are doing, right? Let me look at what does separate mean? Physically disconnected, or there is no path from S to T? There is no path from S to T, and that is what separate mean, right? Can we find the cut edges? Yeah, we find the cut edges by doing that. I already answered that, sorry. This will give you a unique min cut. Can you count number of min cuts? Counting the minimum number of min cuts is a different story. It is going to be a little more complex, and I'll have to think about that problem. You can find a solution for that as well, right? But I'm not sure if it's going to be sub-exponential, but that is going to be a complete different story. Of course, the minimum cut is not going to be unique because in the graph that we have seen in before, I can also cut 6-1 or I can cut 5-2, right? Both of these cuts are min cuts, right? So it's not exactly that the min cut is unique, but yeah, I'm not sure how to see all the min cuts, right? Did you all understand this? Just give a thumbs up if you understand how to find the minimum cut edges, right? And to see if you do truly understand this, this is also a really simple problem. I'm going to be creating a poll here, right, of 90 seconds. So you can answer. Let me actually check what the answer is. So yeah, I'm going to create a poll, the correct answer, and the poll is going to be of 90 seconds. So you can think about the problem and finally just answer whichever one you think is correct. Uh, right. So there are still around 40 seconds. So yeah, just for the people that have not answered yet, you have 40 seconds. A little hint I try to say that the max flow in this particular example, we have seen this example before as well. Max flow was uh, had the value of 10, right? So we're just trying to find the minimum flow here, minimum cut here. So try to find some edges whose sum is 10. Right. So majority of you selected the correct answer, which is C, right? If we select A, B, A, C, S, D, right? We are going to cut this, and we are going to cut this. Right? This is a cut, but this is not the minimum cut because the max flow was 10. This is here the value, the sum is going to be 8 plus 4, which is 12. So this is not the minimum cut. And some people also selected A, which has the sum equal to 10, right? Let me show those edges: A, B, C to B, and S to D, right? So this has this also actually does not have the sum to 10. I'm not sure why did you all select this. Acha, D to C, sorry, this one, right? So this has sum as 10, but I can find a path from S to A to C, and C to T. So this is not a cut, right? This is just some set of edges, which is not a cut, right? So the minimum cut here is exactly A to B, A to C, and D to C, where the sum is 10, and also this set is going to be separated from this set, or the source does not have any path to go to T, right? So now I'm going to give a problem, right? Again, give an example of where we require minimum cuts, right? You can of course think of many standard problems, but I'm going to give a problem that I found really interesting. This was also mentioned in 2016 IPC, so I was watching that video and I really liked this problem. So I'm going to be sharing that. This problem, right, has some people. There are, let's say, n people, n plus m people, right? Out of which n people like candidate A, right? M people like candidate B. So there is going to be an election sort of. N people like candidate A and M people like candidate B, right? And out of these n m people, right? Out of these n plus m people, there are also going to be friendships. Basically, what do I mean by friendships is, let this be S1, right? And let this be S2. So a friendship is a ordered pair basically, right? Such that I comma j, right? Where the candidate, the ith candidate from the set 1, right, is a friend with the jth candidate from set 2, right? And what this friendship means, we are going to see afterwards, right? So basically these people are going to vote, right? The people who like candidate A would prefer to vote to A. The people who like candidate B are going to prefer to vote to B, but they can vote for the opposite candidate as well. A person from set 1 can vote candidate B, and a person from set 2 can vote candidate A. We want to find the number of minimum faults, right? Minimum faults, or the minimum number of penalties, right? Try to think in terms of penalties. So the minimum penalties, where a penalty can be of three types, right? One type of penalty is that person of in set 1, right, votes for B. Another type of penalty is another type of penalty is as person from set 2 actually votes for the candidate A. And the third type of penalty, which is related to the friendship that we just talked about, that I comma j pair, right, votes for different people. Basically, if this ith person in set 1, right, if this ith person votes for A and the jth person votes for B, then that is called the friendship is going to break, or there is going to be some hate developed there. So that is also a penalty, right? We do not want friends, like mutual friends, to vote for different people, right? So we just have to find the minimum number of penalties here. Did you all understand this question? And should I also, give an example and explain what is happening here? Or did you all really understand this? Let me have a poll for that. Give true if you want me to have an example, right? Alright, so just let me give you an example as well, right? A short example, not it's not going to take much time. So let's say we have one person here, second person here, third person here, and a fourth person here, fifth person here, sixth person here, and there are some this is the candidate A set and this is the candidate B set, and the friendships are like one is a friend with 4, one is a friend with 5, and 3 is a friend with 5. This is the friendships here, right? So what is going to happen here, let's say nobody switches for the different candidate. 1 votes for A, 2 votes for A, 3 votes for A, 4 votes for B, 5 votes for B, and 6 votes for B. So in this case, right, in this case, the number of penalties is going to be 3, right? Because this friendship is going to break, this friendship is going to break, and this friendship is also going to break. Sir, friendships can be between same set now. Yeah, the friendships can be between the same sets as well, but to simplify this problem, we are including only the friendships between different sets of pair, right? So we are only talking about the friendships that are between different sets, right? So a person of set A is going to be a friend with set B. We are not talking about friendships between the same set, right? So yeah, here the minimum, the penalties is going to be 3 if all of them votes for exactly which candidate they require. Let's say 5, because he has 2 friendships in the set A, he's going to change the candidate he's going to vote for, and he actually votes for A, right? So these edges that were going to break before are not going to break anymore, because these friendships are conserved. But there is a penalty here, right? 5 actually likes B but is voting for A. So here the number of penalties is 2, right? The total number of penalties here are going to be 2. So also, let me check. Yeah. So do you all understand how to model this as a minimum cut problem? Did anybody understand how to model this? Because I couldn't at first, right? So this is a really interesting problem to model as minimum cut, and in the final problem, the question boils down to that we just have to find the minimum cut of the graph. So just give a confused face if you cannot model it right now, or just give a thumbs up if you think you can. Right. So many are confused faces. Let me give the modeling right now. 1 minute. All right. So if you require 1 minute, let me give you 1 minute. Why can't you just add path with weights 1 for each penalty? Add path with weights 1 for each penalty. And then we are trying to see for minimum cut. Yeah, that is what I think what we are going to do, right? Not I think, that is closely related to what we are going to do. But the exact thing that we are going to do, right? Maximum independent set in this graph. You can try to think in terms of that, but basically we have to boil it down to a minimum cut problem, right? So let us not go into independent set or that sort of stuff. Maximum independent set. Yeah, that is what going to happen, right? So let me tell you how to model this as a minimum cut problem, right? Let's say there is a source node here. There are going to be the nodes from A and the nodes from B, and there is a termination node, right? I'm going to add an edge from the source to each node in set A with weight 1, right? Then I'm going to add an edge of weight 1 for each friendship, right? So let's say this one is friends with this, and this. This node is only friends with this. This node is only friends with this. This node is actually friends with 2 people. This is friends with this one, and this is friends with this one. All of these edges have weights 1, right? And then finally, I'm going to add an edge from the final B set to the destination, right? So the minimum cut in this problem, right? In this problem, the minimum cut is going to be our answer, is going to be the number of penalties that are going to happen. How, right? The intuition is kind of not very clear here. How is this happening, right? If I'm cutting this edge, what is actually happening? And if I'm cutting this edge, what is actually happening? So let me talk about that. So let us see a simpler example like this, right? Source. Let's say there is only one person in A, there is only one person in B, and then there is a destination. These two are dummy nodes, right? So here is an edge of weight 1. This is edge of weight 1. There is an edge of weight 1. So if we are here, the minimum cut is either cut this or cut this or cut this, right? Any one of these cuts is minimum cuts, right? And it would block the flow from S to T. Basically, there wouldn't be any path from S to T. So if we decide to cut this, that means that this node, this edge is connected to, right? This node is now not choosing A, but it's choosing B as the person he's going to vote, and this is choosing B, and this friendship is also maintained, and this edge corresponds to B choosing B. That is also going to maintain to be maintained, right? If we decide to cancel out this edge, then that means that this node is selecting A as its candidate, and this node is also selecting A as a candidate. This friendship is maintained, and this edge is also maintained. Basically, this node is selecting A as its candidate, right? And if we cut the middle edge, that means that this friendship is going to break, and instead he's going to just vote for A. Basically, this edge is maintained, and he's just going to vote for B. That means this edge is maintained, right? Did you all understand this? How this is happening? Just give a thumbs up if you do understand how have we modeled the problem to a minimum cut finally, right? So basically this the explanation that I have given in just a simple graph of containing only 4 nodes, we can expand this in this messy graph as well, and the idea would still apply. Cutting an edge here would mean that this is going to be voting for B. Cutting an edge here is going to be meaning that this friendship is going to break, and cutting an edge here would basically mean this is going to vote for A, right? And finally the minimum cut is going to be an answer. What if there are certain conditions given, right? Let's say this person doesn't want to vote for A at all, right? What if in this question there are given that there are some certain people who are just really stubborn, right? Let's say this node and this node and this node are really stubborn, and they just don't want to vote for A. They're always going to be voting for B. So how do we incorporate that into our modeling? How do we incorporate that in the model that we have created to find the minimum cut? Can anybody of you answer that? Just type it in the chat so that I can break their incoming edges. Then don't keep an edge between B and T. Don't keep an edge. No, that would actually create the opposite effect of what we want. Break the edge to T, add more edge weight. Yeah, that is what I want to hear, right? If we break this edge, then the minimum cut is going to be 0, right? The minimum cut is going to be 0, and basically what we are trying to say is that the penalties are 0 here, right? This is exactly the opposite effect of what we want to create. Now this person is going to be voting for B, this is going to be voting for A, and our algorithm is saying that the penalties here are 0, but we can see that there is a penalty here, right? So what we are instead going to do is we are going to increase this edge weight to infinity, right? Or just a really big number, right? Such that we cannot break this edge, or breaking this edge would make our penalty infinity and would let us know that this system is inconsistent, right? This system cannot happen actually, right? So here we have to always think about it penalties. All of these edges that we have added, the capacity there is basically the penalty that we want to impose on this edge, on breaking this edge, right? So the penalty that we want to impose on breaking this edge is actually infinity, because we do not want this edge to break ever. So we are going to increase its penalty to infinity, and then we can model the same problem. So a simpler problem, let us say that the friendship actually what I said about before, that A and B are both going to be angry, right? In the first part, when A was choosing B, he actually there is a confused phase. Did you all understand the concept of keeping this edge weight as infinity? Did you all understand this? Just give a thumbs up if you do understand it. Let me check that before. There are some confused phases, right? So basically, let me put it as this sort of way, that the edges that we are creating are not the possibility of this breaking down. They are the penalties that we want to impose in this edge, right? Keeping edge weight is equal to infinity means we will never never ever will it limit the flow, hence shall not be a part of a cut, right? In here basically this will never limit the flow that is going to create, and hence it is never going to be a part of a cut, right? This is also a good way to look at it. When we were selecting the minimum cut, we were only selecting the edges that were totally consumed, right? That were limiting our flow. So if we keep the edge weight here as infinity, that means it is never going to limit our flow, right? And that means basically it is never going to be a part of our minimum cut, and basically that means that we are never going to cut this edge, right? So let me go on to a simpler problem, and maybe you could understand it. Let us model this question a little different. So instead of finding minimum penalties, we're trying to find the minimum number of angry people, right? And what do I mean by angry people? Basically, here this person is selecting A. In this question, in this part, this person is angry, right? So we have one angry person here, which is 5, right? But also this friendship is breaking, right? Because 1 is selecting A and 4 is selecting B. So here there are 2 angry people. This is also angry and this is also angry, right? So there are 3 angry people in this example, right? One, because he's selecting a candidate that he doesn't want. Because of that, he can become angry. Or if a friendship is breaking, both the people on both the sides can become angry. So how do we model that now? The solution is really simple, right? Just type it in the chat again. Sad. Do you mean that the friendship is going to break? That is going to be sad. Funny. Increase weight to 2, right? As Chandra says, here the friendship weight is not going to be 1 anymore. Let me put this as 1, right? It's now going to be 2. So for all of the edges that we added in between, right, that is actually going to be 2 here, right? Because breaking a friendship actually means making 2 people angry at once, right? So now the friendship edge weight is going to be 2, and finding the min weight here, right? Finding the min weight here in this simple example, cutting an edge here basically means this person is going to vote for B. The penalty is going to be 1. Right? Similarly here, this person is going to vote for A and the penalty is going to be 1. But if we decide to cut here, that means this person is going to vote for A and this person is going to vote for B. But both of them are angry still because the friendship is broken, right? So the number of people angry here are 2, and the the cut here, the cut value here is also 2. So that is equal to the number of angry people, right? Did you understand how we have modeled this question now? Just give a thumbs up if you understand this. Won't this overcount if 2 edges from a single vertex are present in the minimum cut? Won't this overcount if 2 edges from a single vertex are present in the minimum cut? Basically, it is going to overcount if this is also included and this is also included, right? Because he was already angry. Yes, it is going to overcount. Yes, I'm sorry, I didn't think about that. But let me. I think you were talking about this, right? So he's going to become angry twice. I'm sorry, I'm really sorry about that. I didn't think. I was trying to frame this question about this concept that we can change our edge weights as well, right? But I didn't fully understand the question. Maybe you can think about uh, uh, each person also has a meter of how angry he can become, right? And he can become 1 units of angry or 2 units of angry or 3 units of angry, and we are going to be summing all of those units of angry, and we want to minimize that, right? I'm sorry about that. Yes, Anubhav, this is going to actually overcount if 2 edges are broken from the same node. So let us say if he's this friendship is broken and he's also not choosing for the person he's like, then he has actually 2 units of angry, right? He's not just angry once, he's twice as angry. And then we are going to be summing up that, and we want to minimize that. In that kind of problem, this is going to be alright, right? So the basic concept or the modeling of any problem in a flow problem, that is the main part, right? The main part of the flow problem is trying to model a problem into a flow problem. After that, you can use any of these 4 algorithms as a black box kind of, right? You just basically put these whatever flow model you have created into these algorithms. These algorithms will give you back the value or the edges or the flow paths or anything like that, and then you can just output in the answer, right? But these algorithms, let me talk about them a little and also see their implementation, right? So the Ford-Fulkerson algorithm, we have seen how that works, right? Here the time complexity is going to be how much? It's going to be W into E, where W is the max flow finally, right? The Edmond-Carp's algorithm, what it does is it's just a slight adjustment from Ford-Fulkerson algorithm. There are also other flow algorithms, but I'm talking about these four because these four are generally used, right? Edmond-Carp's algorithm, it has a time complexity of V square E, I think. Just let me check. I'm sorry, it has a time complexity of V E square, right? Here V is the number of vertices and E is the number of edges, right? And what this algorithm does is in each round, it doesn't arbitrarily choose a path. It chooses a path using a BFS, right? That is a simple thing that it changes. It only chooses a path using a BFS, and that reduces its time complexity from big O W into E, which can be very large, to big O V square. Again, this is the worst case time complexity, and usually the time complexities are much lower than this, right? But there can be cases where the time complexity goes to big O V E square, right? So how does this time complexity get reduced by choosing an arbitrary path to a BFS? Uh, well, basically the intuition here is for each edge, right? Each edge is going to get basically saturated or completely used uh, when we have a round, right? Each round is going to make an edge completely saturated, right? And basically uh, there can be V paths before an edge gets saturated, right? Let me talk about this uh, properly. So here is a source, here is a destination. Let's say this edge is supposed to be saturated. So basically the intuition here is this edge, right? This edge is going to be saturated in at most V rounds, right? Because there are V possible paths here. There are at most V possible paths here. So this edge is going to be saturated in at most E rounds. So for E, how many rounds are going to be conducted? A total of V into E rounds are going to be conducted, and not rounds more than this are going to be conducted. And for each round, the time complexity of BFS is also going to be multiplied. So that is E, right? So this is the total time complexity. Edmond-Carp's algorithm. Then there is a push relabel algorithm, right? Push relabel algorithm, what it does, this also works in lots of problems because the random case time complexity is really less, right? Actually the time complexity here is big of V cube, right? But actually here the time complexity is much less than that, right? So what push relabel algorithm does, Edmond-Carp's was just using a BFS. Push relabel is a little more complex. So let me add new slide. So push relabel. Basically it is from the source, right? Let's say there is a weight of h weight 10 here, 11 here, 12 here, and at the destination let's say there is 5, 6 and 2 only, something like this. But what our push relabel algorithm does, it doesn't care about that the flow at the end points is going to be less, right? It starts out with flow being 10 here, it starts out with flow being 11 here, and it starts out with flow being 12 here, right? It goes to this node, and from this node it has the outgoing flow as 5, the outgoing flow here 6, and the outgoing flow here as 2, right? So basically what it does, it then goes back and remove these flows as 5 and 6 and 2. Something like this. Basically, how it is implemented based on an access function and a height function, right? We are also trying to pick the greatest height node first. So there is a push relabel algorithm that works. I had initially planned to, properly explain it, but as the time is a little less, so I'm just going to give an intuition on how the push relabel algorithm works, right? And then we are going to go on over to the scaling algorithm, right? So the push relabel algorithm basically first calculates the heights of each node, height from the destination and not from the source. So T here, right? Let's say there is a node coming from this node, right? So this node, let's say X, is going to have a height of 1. This is also going to have a height of 1, right? But let's say there is also a node of capacity 5. There are capacities here as well. From going from x2 to x1, then this height is actually going to be 2, right? Basically, the height of any node x is 1 plus maximum of heights of y's, right? Such that an x to y edge exists. Did you understand that how we are calculating heights? Just give a thumbs up if you do understand how we are calculating heights, right? So a system like this, right? If we have a system like this would have height 0. Let me write this properly. This would have height 0. This would have height 1. This would have height 1. This would have height 2. But this would have height 3, right? Because the maximum height that I can reach from this node is actually 2. So 1 plus max of h of y is 2, right? So 2 plus 1 is 3. So the height of this node or the source is going to be 3. Height is just the length of the longest path from x to t. Yeah, you can also model as that. Height is the length of the longest path from x to t, right? So this is our heights, right? And also the excess function is the excess amount of flow coming on a node. What happens if there is a cycle? There isn't going to be a cycle here. In flow, it's going to be an acyclic network, right? So here, what I want to talk about is this excess function, right? So when the excess function of the source is infinity, excess function is basically the amount of flow coming into this node minus the amount of flow going out of this node, right? So source, we go to 1, we go to 2, we go to 3. Let's say this has float 10, this has float 15, and this is float 10 again. 5, 6, 5, this is the destination. So this is the current flow as well, right? So this would have excess function as 5, this would have excess function as 9, and this has excess function as 5, right? Because there is an excess of 10 flow coming in here and only 5 flow going out, right? So the excess function here is equal to 5, here it's equal to 9, and here it's equal to 5, right? So did you understand what a excess function is? It's basically the flow coming from u to x such that there exists a edge from u to x minus a flow of x to v such that there exists a edge from x to v, right? Initially we declare the excess function of the source is infinity, right? And then what we do is we go from the highest height, right? We sort these heights of each node. We go from the highest heighted node, which is the source, of course. The highest heighted node will be the source, right? Let's say the heights are, or let's say these nodes are ordered in their heights, right? So this is the max height, and this is the lowest height, which is going to be our sink, right? Or the destination. At the maximum height, we are looking at the excess function, which is infinity, and from this excess function we are seeing all of the nodes that it goes to, right? Let Let me just extend the time by 10 minutes, right? So we see that this node, which is a source, go to this node and this node and this node. The capacities here are 10, 15, 20, right? So because this has an excess function of infinity, I subtract 10, 15 and 20 from here, minus 10, minus 15, minus 20, and I give a flow of 10, 15 and 20 to these nodes, right? So this node has now a flow of 10, right? Excess function 10. Here it has excess function of 15. Here it has an excess function of 20. When we come to this node, right? When we come to this node, let's say there is an edge going from this node to here of 20. But here the excess function of this node is only 10, right? Let's say it also has, never mind, right? It only has an excess function of 10, and there is an edge going out from here 20, so we cannot saturate this edge, right? We cannot saturate this edge. That's why we can only give a flow of 10 here from this edge, and now the excess function of this node is going to increase by 10, which is going to be 25. We keep on doing like this, and finally our array is going to look something like this, right? The excess function at the source is going to be some f value. The excess function here is going to be, let's say, excess of n minus 1, n minus 2, let's say, right? Excess of n minus 3 up until excess of 0, right? These can be 0, can be greater than 0. If they are greater than 0, we are going to be from the reverse edges, right? From the edges the flow is coming from, we are going to subtract the flow there to notify that there is some excess flow coming into this node. So subtract this node from the edges from where it came, right? But we are not going to do that for the final node, for the destination, because this is exactly the value of the maximum flow here, right? Did you understand how this algorithm works? Just give a thumbs up if you do understand how this algorithm works and also understand the intuition behind this algorithm, right? Basically, we're trying to pressure all of the reservoir tank we have in each of the nodes, right? And if those nodes do not have the capacity for such amounts of flows, we're going to backtrack and cancel out that flows later. But basically, whatever maximum flow we can give, we are going to give that. And finally, whatever the flow that comes in the final part, that is going to be our f, which is the most used algorithm. The most used algorithm, I would say, many people use push relabel. Many people use Dillex algorithm as well. Personally, I use scaling algorithm the most because it has a time complexity of big of e square log c, right? I'm going to be log c. Let's call that as log w, right? I use this algorithm, right? When it's a kind of a sparse graph, right? When the number of edges are not much greater than the number of vertices, right? Then this algorithm would work the most. And when the number of edges is really large and the number of vertices is small, right? When it's a dense graph, push relabel algorithm also works as well. There is also a Dynex algorithm which many people use, but I'm not going to talk about that right now because it's really complex, right? So let us talk about the scaling algorithm, and because there is not much time to explain the implementation, I'm going to give one overview of the implementation in my code editor, and I'm also going to be sharing the implementations at like the Discord channel. I'm going to be sharing the Discord server link in a while, right? Right. So in here, in the scaling algorithm, what we do, right? In the scaling algorithm, we do not look for minimum. Right now, we were in Ford-Fulkerson algorithm. Try to remember Ford-Fulkerson algorithm. The scaling algorithm is just improvement from that, right? What it does is we were trying to look for any path that has greater than 0 weight, right? We were trying to find any path which will give us any amount of flow, no matter if it's 10 to the power 6, no matter if it's just 2 units of flows, right? we have to change as per goal. Like me, I have chosen two algorithms. One is the scaling and one is the push relabel, right? You can choose between these two. But of course, knowing about this algorithms helps to model the problem as a, flow algorithm. So yeah, you should learn about all the algorithms, but you can stick to only one or two algorithms, right? So the scaling, not theorem, algorithm. What it does, in the Ford-Fulkerson algorithm, we do not try to find a path that has a value less than some c. We choose a large c, right? We choose a large c, and we only try to find paths which have flows greater than c, right? Let's say I choose c as let's say 4. That is not really big, but let's choose that as 4 currently, right? So let's construct a simple flow path. It goes from 2 to 2, it goes from 1 to 3, and here as well it goes from 1 to 3 with 3, right? This is the source, this is the destination. So here I have selected C to be 4, right? So I'm not going to select any path, because if you look, this path has the minimum weight as 1, and this path has minimum weight as 3, right? So I'm not going to select any path in this particular section, right? I'm going to skip this round. I'm going to say, all right, the Ford-Fulkerson algorithm for this C is complete. Next I'm going to half my C, right? Next I'm going to do C is equal to C by 2. So it's now equal to 2. Now I'm trying to find paths of size 2, right? Let me take back here, right? So C is now equal to 2. I just halved that value, right? If it's odd, you can select any floor or ceiling function. Better select floor function. It's not going to matter which way you're going to go, right? Just half that value. And then when C is equal to 2, I cannot select this path, right? Because this has flow as 1, right? But I can select this path because this has flow of 3, right? So as 3 is greater than equal to 2, I can select this part. So what I'm going to do is, let's also add the reverse edges, right? What I'm going to do is subtract 3 from here, add 3 to here. So this is going to turn into 3. And this is going to turn into 0, right? So now our algorithm at this part. Can I find any other path that also has flow greater than 2? We cannot, right? So next we are also gonna decrease our C one more time, right? Half it basically. So now C is 1. Now we can find a path which has a flow greater than equal to 1, right? So which is this path. Subtract -1 here, +1 here, -1 here, +1 here, and finally the flow has come out to be 4, and 1 flow is going from this section and 3 flow is going from this section, right? So this is our final answer. This algorithm works in big O of E square log C time, right? And C you have to select the maximum flow that you can possibly have. So it's generally a nice idea to select C as the sum of all the capacities, right? Sum of all the capacities, because the flow cannot be greater than the sum of all the capacities, right? So just select the sum of all capacities, or you can also optimize the value of C if like there are many ways to optimize the value of C. But basically select some C and take a because we are halving at each point, it's coming out to be E square log C. This also depends on the final flow, right? Just like the initial Ford-Fulkerson, where the time complexity was big of E W, right? C is always going to be greater than or equal to the W, right? So this also depends on the final flow, but here the time complexity is considerably less. This is still polynomial time complexity, right? This is not pseudo polynomial time complexity. Division 2 in 2 minutes. will watch recorded. Oh, there was a division 2 in 2 minutes. I'm sorry about that. Yeah, so let me you can see the recorded videos afterwards. Let me just show the time implementation, and then I'll be sharing the implementation in the Discord server. So let me just link the Discord server so uh, people can find this afterwards as well, right? So this is the Discord server that I'm sharing in the chat right now. The people watching at YouTube can pause and just copy this link, right? This is the Discord server link, and this is the link for the practice code page where I selected some problems to be held on this, right? So there are some problems on flows which you can solve in this practice course page. Let me share my code editor, and yeah, and let me share on YouTube as well, right? So this is the code for Max Edmund Carp, right? The one where we do BFS at each round. So this is the main function where we try to do max flow. Here we do x is equal to BFS of ST. We run BFS until x is not equal to 0, right? When x is equal to 0 means we cannot increase our flow by any amount. This is the new flow that we are getting. So we increase answer plus equal to x, and we change the capacities at each edge, right? We change the capacities at each edge that we require. So capacity of previous of current minus equal to x, capacity of current per previous plus equal to x, and this is basically from this BFS function. BFS is simply running a BFS and also setting the parent uh, nodes from where we have reached to this value, right? So this is running the BFS, and this is setting up the capacities after each round. And if you have to change this algorithm to be the scaling algorithm, you just have to change the BFS so that you here basically you're checking the capacity of current plus next is greater than 0. It's just not equal to 1. Instead, you put a W here and you change the W after each round, right? This W is supposedly the sum of all capacities first, and you also put a parameter of W here, right? And just logically changing this W value after each round will give rise to the scaling algorithm, right? The push reliable algorithm is different, and I'm going to be sharing the implementation in the Discord server afterwards. So please do join the Discord server, because it would be helpful to know when the next class is going to be held or if any announcements are to be made, right? All of the communication is going through that. And yeah, after this, there is a class tomorrow at 12 noon, which is going to be on FFT. I'm going to be covering that. It is also going to be a 2-hour session. So hope to see you there. And let me just close the stream, right? If you do have any